Today in the lecture 2 of module 4, we shall be discussing cement and cementitious material. In the last lecture, we discussed about cement and its hydration. Today we will look into some of the other materials as well. So, general outline of the talk would be types of cement, because various types of cements are possible. We only talked about ordinary Portland cement yesterday. Then we will just mention about lime and then look into supplementary cementitious material such as fly ash, slag, silica fume, etc. There are several others. We will discuss mainly these three, although mention a few. Right. So, let us look at types of cement. Right. So, what we discussed yesterday was ordinary Portland cement, and we have also seen that various compounds of the cement, namely C3S, C2S, C3A, they have different roles. For example, C3S gives early strength, whereas C2S gives long term strength. C3A on the other hand increases the heat of hydration and susceptibility to sulfate attack in the long run. Now, therefore, by modifying the composition of the cement and also by modifying their physical properties, performance of cement can be changed favorably to obtain different types of cement. Let us see how do you get them. So, OPC we have discussed, and we have also seen what is a rough composition in terms of oxides or in terms of compounds in them. Then this next important class of cement or type of cement is RHPC. RHPC stands for rapid hardening cement. RHPC stands for rapid hardening cement. It stands for rapid hardening cement, rapid hardening cement, rapid hardening cement, Portland cement. So, if you see that it must harden rapidly, that means if I want high early strength, this cement I am going to use. And how can I do that? Well, the chemical way, first chemical way would be to increase C3S, because C3S gives the high early strength, and the physical way would be grind it to a finer particle sizes, because finer the particle sizes, its reactivity will increase. It will react at a faster rate, because reaction of cement is through its surface. So, if you increase the surface area, reaction rate will be faster. So, in case of rapid hardening cement, setting characteristics will remain same, but I want its strength development to be early, which we can of course get by some other means also, like steam curing I mentioned yesterday. But if I want to get it through a cement, it will be rapid hardening cement. So, in this cement C3S content is generally more, its fineness is more, it is grinded to a finer, more finer particle sizes, right. Now, there can be very rapid hardening cement or special rapid hardening cement, something like jet cement. A jet cement is one which will actually harden very quickly, even setting time may be relatively small, less than 30 minutes sometime, 1 to 30 minutes can be there, but they are specifically used for repair purposes. And this specific cement, jet cement, is produced with OPC plus calcium fluoroaluminate and some sort of retarder such as citric acid. So, this is a special cement. So, there could be special cements which you require, let us say in an airport runway, you can't stop the traffic, you immediately want to repair it, you would require very fast hardening cement, and jet cement or special RHPC of various kind, they can be the solutions there. Where do you use otherwise simple RHPC? Where I want high early strength development. Say for example, as I mentioned yesterday, if I want to release the mold very quickly, then I would use I use rapid hardening Portland cement. Okay. So, this is one type of cement commonly used where I want quick strength. Of course, I can also use steam curing together with that to get still higher strength. So, this is one of the solutions, right. So, this is one type of cement. low heat Portland cement. Now, remember, if you are increasing the reaction rate, heat of hydration will be higher. So, rapid hardening cement RHPC will have high heat of hydration. So, one must remember this, right. But all places I can't, if all structures cannot tolerate high temperature or high heat of hydration, development of high temperature in the early stages, or heat of hydration should be relatively less in some sort of structures, particularly in mass concrete, in massive structures. Why? Because in mass concrete, where you are doing a bulk of concrete, something like a dam, let us say a gravity dam, where the thickness is very, very large. Now, here what will happen? Heat of hydration, if it is high, then it will not be dissipated fully, because it gets dissipated only through the surface. So, what happens? Surface becomes cooler and inside remains still warmer, because all heat has not been dissipated. A lot of heat of hydration came, rate of hydration was pretty high, it immediately in the beginning itself came lot of heat, and this hot heat is, if not dissipated, it will remain stored inside. So, outside when it is cooled, what will happen? The outer surface, it will actually shrink, but inside still being relatively hotter would not shrink, resulting in a restraint to the shrinkage of the surface. What does it mean? The bottom is warmer, not shrinking, but top is trying to shrink, and this may result in cracking at the surface. Anyway, so that is why heat of hydration has to be controlled in some particular structures, and there you use low heat Portland cement. Then what should we do? Low heat Portland cement surely will have lesser of C3A, lesser of C3S, will have less grinding, the opposite of the previous one. Of course, there are other means of getting low heat cement also, we shall see later on, but essentially it will have less, it should have less rate of reaction in the beginning, and therefore C3S you reduce down, increase C2S, also reduce down C3A, and should not be grind to a very high level. Sulfate resisting cement. Now, these sulfate resisting cements are used in places where sulfate is a problem. Let us say groundwater contaminated with sodium sulfate or any other sulfate. We will discuss about sometime later on about the sulfate attack, but one thing I have mentioned yesterday in the last lecture, that sulfate attacks C3A, tricalcium aluminate. It reacts with sulfate, gypsum, which is calcium sulfate, forming a trangite, and which expands in volume. This volume expansion causes cracking of concrete, because in a hardened concrete, if something is trying to expand, it will essentially mean that is actually causing disruption of the or cracking of the concrete. So, because it is trying to expand, it has got no space to expand. So, that is why sulfate attack, the component in the cement, the compound component in the cement that is responsible or that helps in sulfate attack is C3A. So, we actually reduce down the C3A content to make it sulfate resistant. So, sulfate resisting cement is the one which has got less C3A. Then we have got this new class of materials or cements, they are called blended cements. So, these blended cements are cement, OPC cement blended with pozzolana. We will come to this pozzolana when we talk about supplementary cementitious material. Maybe one pozzolana, maybe more. So, you can blend the cement with some other material which are helpful, which are supplementary cementitious material, like cement fly ash is a pozzolanic cement, OPC, PPC, Portland pozzolana cement, like OPC ordinary Portland cement, Portland pozzolana cement is a blended cement, where fly ash may be the blending material. Somewhere you can have slag cement, blast furnace slag cement. So, that is again slag blending and so on. So, therefore, we can blend, and we will understand its action when we look into the supplementary cementitious material more. Now, this blending does two things. One, it reduces down the clinker, use of clinker, which means sustainability increases, lesser carbon dioxide emission to the atmosphere. So, you are using the cement judiciously. It will be cheaper also if the ash, for example, is available with very little transportation cost. So, it can even be cheaper, and they have some positive effect in terms of concrete properties. So, blended cement are the other class of cements which are going to which are there, and it is very likely that in future, because of the sustainability, environmental sustainability, concern of energy and so on, this cement is likely to be more and more popular than any other cement. Of course, every cement has got its specific use. This is a special class of cement called supersulfated cement. About 80 to 85% ground granulated blast furnace slag mixed up with 10 to 15% of gypsum and hydrite is called dead burnt gypsum, and 5% of OPC and grinded together. So, you see it has got large amount of slag, blast furnace slag, GBFS, granulated blast furnace slag, and this granulated blast furnace slag plus 10 to 15% of gypsum. So, gypsum and slag together is this formed. So, this one because it's this already gypsum is already there in the system, and this one is highly sulfate resistant. So, this is a special cement used for high sulfate resisting area where you have high sulfate content. Now, interestingly, sulfate resisting cement which I mentioned earlier is not good in case of seawater. Seawater also contains sulfate, both calcium sulfate and magnesium sulfate, but it also contains chloride. So, where sulfate and chloride are present together, sulfate resisting cement is not so good. Just by reducing C3A content, you do not get a proper cement. But supersulfated cement, it gives you adequate protection against both sulfate attack as well as chloride ingress and corrosion, etc., reinforcement corrosion. Chloride or seawater attack, one of the major problem is of course not directly attack onto the concrete, but attack onto the reinforcement inside, corrosion, rusting of steel. So, this cement is good for both this purpose. So, very high durability of this cement. White cement, for aesthetic purpose, this is a cement. In its production there should be no trace of iron oxide, because that sort gives colors. So, therefore, what is used? China clay and chalk. I mean, one combination could be China clay which is white colored clay, and chalk, calcium carbonate, very little oxides, iron oxides in this. It should not be contaminated with such oxides which will give color. So, it is a little bit costly, or other pigmenting agent can be added to give color to the cement. Expansive cement which expands, normally cement will shrink. So, supposing you want to fill in a grout hole, some hole you have made, or in repair works you have made some hole, you want to fill it, old concrete is already there, you have made a hole, and now you want to fill it with something. Now, this should be done with expansive cements, or shrinkage compensating formulation. Now, this uses again gypsum and C3A. Action of gypsum and C3A in its fresh state, in the soft state, in the plastic state, they cause expansion, therefore, they compensate for shrinkages. So, these are some of those types of cement. There can be several other cements possible, several other cements are possible which I have not discussed, but the main types are here. Let us see what happens to their strength characteristics in the next slide. Okay. Now, this is as per the American Society of Testing Material Classification. In the IS 450, IS 269 is the code. We have codes for cements, and cements are 3 grades in Indian situation: 43 grade, 33 grade and 53 grade. 33 grade, 43 grade and 53 grade. 33 grade is one which attains 28 days strength of 33 MPa. 43 grade is one which attains 43 MPa 28 days strength, and 53 grade of cement is one which actually attains 53 MPa strength on 28 days when you test the cement in a standard manner. Now, how do you test the cement? You test the cement making cement mortar cube of 50 centimeter square base area, 50 centimeter square base area. So, what you do is you make cubes with the base area 50 centimeter square. So, area of the base or any area, all this area equals to 50 centimeter square. So, you actually make cement sand mortar cubes 50 centimeter square base area and then crush it under load in a standard manner. That is how strength of cement is measured. Now, sand is standard, the amount of water you add is also standardized in terms of standard consistency I mentioned earlier, which will give you right kind of flow. Standard consistency will make it a uniform consistent mix and give a right kind of flow as well. So, that is what is standard, the amount of water that would be added is related to standard consistency. And you test this cube in a standard manner at standard rate of loading. So, preparation is standardized, curing is standardized, vibration, everything is standardized, the sand that you are using is standardized except for the cement. So, therefore, this gives you the relative measure of the strength of cement, how good it would be when used in concrete. It is a relative measure, they are not absolute, you can't, it is not possibly very wise to relate concrete strength directly to cement strength, although it is sometimes done, but it is definitely a relative measure of which cement is better than the other from strength point of view. So, we have 3 grades of cement, 33, 43 and 53. 33 grade of cement is one which gives you 33 ampere strength at 28 days age when tested in the standard manner. The standard mortar cube is tested in standard manner. This is 1:3 cement sand mortar cube and sand is again standard. So, everything is standardized except the cement part of it. 43 grade is one which gives 43 MPa on 28 days at testing. When you test at 28 days age under specific rate of loading, everything is specified. So, those are the 3 types, and this corresponds to type 1 cement is the OPC cement as far as the American Society of Testing Material is concerned. We too have rapid hardening cement, we have low heat, we have rapid hardening cement, sulphate resisting cement, and also we have Portland pozzolana cement, Portland slag cement. These are there all in Indian standard code. Indian standard codes are there for all those, but very popularly all over the world this ASTM type 1, type 2, type 3, type 4 and type 5 are used together with other types IP etc., which I think I will not go into details of this. But just the point that I wanted to mention is the compressive strength of cement when you get from different cement types, right. You can see that type 1 which is the Portland cement is here, type 1 is here, its strength development is there, type 1. Type 2 is modified, which is somewhat low, between low heat and OPC. So, it does not gain strength very as good as OPC, but slightly less, but it has got less heat of hydration. So, you can see the type 2 would follow, type 2 is very close to this, type 2 is here, type 1 is this, type 2 is here, type 2 is here, and type 3 is nothing but rapid hardening cement, type 3 is the rapid hardening cement. So, RHPC. Type 4 is the low heat cement. So, type 4 is a low heat cement, and type 5 is sulphate resisting cement, and type 5 is sulphate resisting cement is here. So, you can see that rapid hardening cement, although it gives you very high early strength, relatively higher early strength, but on some days around 90 or so its strength actually is lower than the other cements. Okay. OPC of course is better than rapid hardening cement, it will have much better strength than anything else, right. And then low heat cement, that low heat cement on the other hand, type 4 shows low strength in the beginning, but in the long run it shows higher strength. So, this diagram shows you how the strength development takes place. Now, you can understand the same thing. How do you get rapid hardening cement? We get it by grinding it more and increasing C3S, reducing the C2S. So, what we do? We actually increase the high strength, but when we are reducing the C2S, long term strength would be relatively less. So, if you increase C3S, you get high early strength, all right, but long term strength will be affected. If you grind it more, rate of reaction will increase in the beginning, but what about the final? Final situation is ultimately it is not going to affect. So, final strength is lower in case of rapid hardening cement. So, you get initially high strength at the cost of long term strength, and that is what we have seen in other cases also. When we use steam curing, we get high early strength, but in the long term you do not get strength. So, if you want to get very high strength early, it would affect the long term strength. You can't have both together, both high early strength, it is not easy to get that. So, that is the point, and that is how it is. And in case you want to reduce down the rate of reaction, well, in the long run there will be uniform structure and you will have much higher strength in the long run, right. So, that is what the type of various types of cement and their strength development is concerned. If we look at the durability or other issues, setting characteristics by and large should not change. Setting characteristics of all these cement should remain same. That means, I must have at least 30 minutes available for placing my concrete, because initial setting time is related to placing concrete. I can disturb the concrete within that period of time without actually disturbing its final properties. So, we can remold, mold and revibrate, things like that, we can do that, actually vibrate it or handle it during that period of time. So, initial setting time I need a minimum 30 minutes, during which I will handle the concrete, place and compact. Now, this is more or less same for all the types of cement, and final setting time also should not be more than 10 hours, because I got to remove the mold after that. So, the maximum limit is this. So, by and large this should remain follow this, but we must understand, if I want to take out the bottom support from the shuttering, low heat cement would require longer period of time to shuttering, the support to the shuttering of the bottom shuttering of a slab, let us say, should be kept for longer period of time if you have low heat cement. So, where you have reduced down the rate of reaction, all these issues comes in, and one has to take a judicious decision at the moment of planning, design, as well as at the site when you are using what kind of cement, depending upon the type of cement. We have also seen that this might have some effect on the curing, because the one which has got lower rate of load, rate of strength development may require slightly higher curing. Long term durability obviously would be better of the low heat type, because where it will have a much uniform structure compared to this, but then this one can design system even with RHPC durability situations, you have to take care of it, design it by design you have to take care of it, not by default, but by design you can take care of things. All right. So, this is something about the type of cement. Now, let us look at another material, lime, a little bit. This was historically used very much. I would have mentioned it earlier that all the monuments all over the world actually used lime in some form or other, either the hydraulic lime together with clay using what is known as pozzolanic reaction, or the lime which is non-hydraulic lime. So, this material was historically used, all the monuments all over the world used this material, and of course, cement came and replaced this material very much, because cement is much more versatile, much higher, quickly you can get the strength. There are many more things can happen with cement which is not possible with lime, but still lime is used for repair of historical monument, to match historical monument, to match the monument, to match the properties of original material, because originally lime might have been used, and that is why it is, right. Okay. Two types of limes, as I said, hydraulic and non-hydraulic limes. Two types of limes are there, hydraulic and non-hydraulic lime. So, this is hydraulic lime, non-hydraulic lime. Now, non-hydraulic lime sets when excess water evaporates from him. What is the mechanism of non-hydraulic lime? Actually, it is calcium hydroxide. It will be calcium hydroxide, and then when excess water is evaporated from CH, excess water is evaporated from CH, the CH will react with carbon dioxide to form calcium carbonate, and this is a solid hard material. So, it would take long time to harden, but this will harden to this. So, non-hydraulic lime sets and evaporates to give you this. So, this was also used in past in historical monuments. This was non-hydraulic lime. Hydraulic lime, on the other hand, it contains active clay, nothing but silica, and reaction of the clay with lime leads to cementing property. This has been used very largely. Lime surki in India, lime and surki, similar sort of thing. Surki is nothing but the dust that you get below brick kiln. You burn the brick in a kiln, and below that the dust, fine dust that goes is surki. So, lime, surki or similar material has been used in past very much. So, this is how lime is used, but right now of course, it is very much used in all sorts of all heritage structures, because originally limes were used and you must replace them by the same material without changing it much, because they can create all kind of incompatibility if you are using a different or modern material without understanding its property. Of course, it is not that 100%, but preferably it should be whatever is the material used, also from aesthetic and from other points of view. Same material must be used to repair, and that is why lime finds its use. But more importantly, lime has a role, although it is not added, but lime has a role in the supplementary cementitious material. The supplementary cementitious material we are talking of, they are mainly the pozzolana. These pozzolenas are nothing, the name it derives from the volcanic ash. Volcanic ash. Now, this volcanic ash in Italy, Europe, actually, you see, there is an interesting thing. This is also clay. This is also clay. Silica. Clay consists of silica alumina. So, volcanic ash, when eruption from volcano takes place, the ashes comes out of it. Actually, they are heated up. The clay is heated up to high temperature, and the fine ash will come first flying up. The heavier ones obviously will come with the lava, right, molten material with other molten material, but the fine ones, dust type, very fine ones, comes out into the sky as smoke or dust, and they get deposited all over. Now, this when at a very heated up clay suddenly exposed to the atmosphere, air temperature which is much lower, they gets rapidly cooled. In the process, actually, you have heated up the clay, so its structure would have changed, and suddenly you are cooling it. The structure that is formed, that has some amount of energy or heat locked into it. So, its chemical potential is higher than a crystalline silica. Quartz, for example, they are crystalline silica and this is not reactive, whereas surki I mentioned earlier or volcanic ash, they are reactive. There are certain amount of reaction capability. They can react, but they do not react with water directly. What they do is they react with lime, because silica can react with lime and they form similar sort of material as CHS gel, what cement produces. You see, in case of cement, we are actually adding lime and silica before burning, and they were burning them together. In this case, the reactive lime and reactive silica, we are, they are reacting later. So, this reaction is called pozzolanic reaction. So, originally the volcanic ash, the name comes from volcanic ash, which shows these characteristics, but there are many other materials which are actually sort of earlier would have been, one would have called them waste product, but perhaps one would call them byproducts like fly ash, which is generated by thermal power plant, or for that matter the slag, blast furnace slag, or even some other slags, copper slags that have been attempted but not as popular. Some other material as metakaolin, rice husk ash, it has to be processed, silica fume which comes from ferrosilicon industry. There are several other products which have similar sort of property, because they are also silica, and silica which can react. Which silica can react? The one which has been possibly very fine, which is very fine, relatively fine, and which is not crystalline, which is amorphous usually, and actually usually once you have heated it up, it has been exposed to atmosphere for a short period of time. So, it could not dissipate all its energy, short I mean years, in terms of years, not in terms of million years, because silica is there, it is in the earth crust in abundant, and many silica do not react, only active silica or active clay can react. So, that is what it is. So, these are pozzolanic material which can react, and essentially they are amorphous in nature by and large. There will be some crystalline component in them, but it is amorphous one which is responsible for reaction, and this can react with lime, producing similar sort of thing as the cement produces with water. So, lime, water and pozzolana can gives you same CHS gel, similar sort of thing which happens, which you find after cement is added to water, right. But only thing is this reaction is relatively slow and generates much less heat of hydration obviously. So, this is an advantage, but the disadvantage is of course, it is relatively slow reaction. So, one of them I have mentioned is the fly ash. Fly ash is a product of thermal power plant. It comes out comes a product from thermal power plant, it comes out from thermal power plant, and it is collected in electrostatic precipitators. So, what happens? Thermal power plant will have coal coming from the mines, may be washed if they want to reduce the clay content of the coal, but usually the coal coming out from the mines will have lot of clay in them. This clay comes together with the coal and this is grinded before burning to fine powders, the coal itself in a whole thing. Only large ones which you can't grind, they are called mill reject, they are thrown out, but rest of the material is burned. So, when you burn at about 1800 degrees centigrade or so, the coal carbon part of it gets converted into carbon dioxide and other oxides would be coming out together like sulfur dioxide and so on, some maybe even NO2 and so on, small quantities they will be there. But what about the SiO2 which has been also grinded together with the coal, the clay part of it, which was there as an impurity in the coal, mined coal, and then it has been grinded together. So, this will also get heated up, but this is already oxidized. So, SiO2, Al2O3, Fe2O3 etc., all this material, they are solid particles, the finer ones tend to come out with the flue gas. The heavier ones of course goes to the bottom and we call them as bottom ash. Well, that is not much of our concern at the moment, although they can also be used in various ways. But the fly ash is what is of our concern at the moment with reference to cement system. This fly ash which comes out of the flue gas, flies away, is collected at, because they are charged particles. So, they can be collected in electrostatic precipitators, ESPs as they are called, ESPs. So, they can be collected in ESPs, electrostatic precipitators, which are charged plates where this charged particle will get collected, and they are collected from these hoppers, ESP hoppers, and possibly should be handled dried, by and large handled dried in dry condition pneumatically and stored in silos for future use. So, this is a material which is again clay, because clay is the impurity that was present in coal, and this clay burnt together gives you fly ash. There are types of fly ash, C and F type. There are two types as per again American Society of Testing Material, ASTM classification, American Society of Testing Material, that is called ASTM classification. C and F, C is the one which has got relatively higher lime content and F is one which has got less lime content. It depends upon the source of the coal, it depends upon the source of the coal, anthracite coal or lignite coal, it will depend upon so it will anyway that I think we will have to stop the discussion at the moment, not too much, but we understand one thing for the time being, that fly ash, a product from thermal power plant, is a pozzolana, and it shows similar reaction. That means it can react with lime because it is a clay heated up and then suddenly cooled, exposed to the atmosphere. The flue gas is it was hot at 1800 degrees centigrade, suddenly it has been exposed to air which is at about 25 or 30 degrees centigrade, and then it rapidly cools, but while rapidly cooling it cannot get crystallized into stable structure. So, it unstable structure which can react, certain amount of chemical potential or chemical some energy is logged which is available as chemical potential. So, it can react with lime to form the CHS gel like product. So, this is one of the pozzolana which is most commonly used these days, and then we have other main pozzolana which is also very commonly used is ground granulated blast furnace slag. Now, this in blast furnace for iron ore also contains impurity clay, because ore, that is a clay is the abundant material in the earth crust. So, it will have SiO2 etc., all this clay minerals Al2O3 mixed up with the iron ore. So, to separate that, what you do, you actually add up lime in the blast furnace, and this lime forms a kind of slag which floats above the iron or the molten iron, and molten iron is taken from the bottom, from the top molten iron is removed from the bottom, and the tops this material molten material of lime and silica etc. are taken out. So, this is what forms slag. This is what forms slag, which is removed, which is taken out from the blast furnace, right. It is removed from the blast. So, this slag, when it is granulated, made into granules and grinded, that is GGBFS. Now, again, since the clay was the impurity and you added lime to remove them, this will have some amount of clay and eventually it will have some amount of lime as well. We shall see the chemical composition in detail a little bit later. So, it will have some amount of lime as well as some amount of lime, means calcium oxide, C in our cement chemistry notation, right, this and this, all these materials will also be there in this one, in the slag, and this materials is same oxides as that of those of cements. So, this can, if you add water, this does not react, but it reacts in presence of an activator. If you have some sort of an activator, this has got similar oxides, although the proportions of the oxides are different, they do not react, it does not readily react with water to form something like hardened stone as the cement does. But if you add an activator to this can actually give you cementitious behavior, it can behave like cement. Since the proportion of SiO2 is quite large in this compared to CaO, there is certain amount of excess SiO2 available and which can act as pozzolana. So, GGBFS is a supplementary cementitious material which comes out from the blast furnace slag. It can be cementitious with an activator, but otherwise, if you add lime to it, obviously the pozzolanic reaction will get. But interestingly, if you add cement to this, part of the cement, you take cement and mix some slag to this, the slag is gets activated by the cement itself, because cements have got certain amount of alkalis, sodium and potassium oxides, the gypsum, etc., which can act as activator for the slag also. So, cement slag combination, they can be a very useful material. And when I was talking of blended cement, you have one cement with slag with OPC, some other cement with fly ash with OPC. So, when we have fly ash or similar pozzolanic material mixed up with OPC, we call it Portland pozzolana cement, PPC, and this is slag cement, this is Portland slag cement, PSC. This would be if I add some amount of slag to the cement. So, these are two kind of blended cements that I was mentioning. Well, you can have composite cement made up of not only simply Portland cement and pozzolana or Portland cement and slag, but you can have some amount of Portland cement with fly ash, with slag, etc. So, all possible cement designs are possible and it is being tried now, composite cements are being tried. So, this is what the blast furnace slag is, the next supplementary cementitious material. And if I look at the next material, by far it is very popular for very high strength matrices these days, is the silica fume, and this material is a byproduct from the silicon industry. It's relatively recent than fly ash or GGBFS, and the silicon or ferrosilicon industry. Now, actually to produce the silicon, what you do is you heat up the quartz and some amount of fumes come out from this process of production of cement. This fume, when condensed, gives you what is called condensed silica fume. This is very rich in SiO2 because it is only quartz that you are burning, and then the fume comes out and that you are condensing. It is also called microsilica, a little bit processed. So, processed microsilica. So, silica fume is the other byproduct coming out from silicon or ferrosilicon industry. It is very rich in SiO2, the silica, and this silica again, since you have heated it up and cooled it suddenly, you see there is certain amount of chemical energy locked into it, and this can react with lime, producing same pozzolanic reaction. We will look into the details of this one. So, these are some. In addition to this, I mentioned you rice husk ash. So, when you rice after husking, the husk that you get, right, this can be burned, and the ash again will contain a lot of silica, and that is to be processed, and this is another material. Similarly, metakaolin is another material which could be pozzolanic. There are other metallic copper slag, for example, has been tried as pozzolanic material, because wherever you have that you have clay and you are heating it up and then you are cooling it rapidly, it is exposed to the atmosphere and the materials are fine that can act as pozzolanic material. Surki I mentioned was a traditional historically used pozzolanic material coming out of burnt clay bricks. So, clay bricks, when you burn, in the bottom some dust accumulates, very fine dust, which actually nothing but clay heated up to high temperature suddenly cool down, and those are. So, all of them can serve as supplementary material, but at the moment first three are the most popular, and we will look more into details of this. Well, first, how do I characterize this pozzolanas? I must do some characterization, whether it is really worthwhile to use it in concrete or not. One thing we do is we find out the grain size distribution. The particle sizes are important. Very coarse particle will not act or will not react with cement, So, the grain size distribution and their fineness, there is various ways of measuring them by simple hydrometer analysis used in geotechnical engineering could be one of the ways, but use such material which use an inert fluid or liquid where you can do hydrometer analysis. There are modern particle size analyzers based on various principles through which you can find out particle size or grain size distribution. Fineness is measured like it is measured for cement. One of the ways is of course the Blaine's fineness, where specific surface is measured. You measure actually specific surface, that is meter square per kg. How much is the specific surface? Surface area of the material per unit mass of the material, or in centimeter square per gram. Now, meter square per kg for fly ash, it minimum should be 180 meter square per kg, but it can be much higher. Similarly, for cement, ordinary Portland cement 33 grade, it should be 225, but they can be still higher. So, minimum is specified in most of the codes. This fineness is usually measured by Blaine's method, where what you do is you find out the air permeability, and from the air permeability how much air is passing. There are more than one methods, but what is most commonly used is Blaine's fineness method. So, you pass air in a specific manner, and from the from the passage of this air you try to find out what is the surface area, because larger the surface area, relative time taken for flow would be higher. So, there is a method of measurement. 1727 IS code gives you this measurement. So, we are not discussing those measurements, but this fineness is usually measured in terms of Blaine's method in the unit of meter square per kg. You can of course find out the surface area or fineness from the grain size distribution as well, but they do not match. Conventionally, this is what is done. This is one of the ways of specifying, characterizing pozzolana. If you have grain size distribution, that also is good enough, but they do not match, not necessarily same values you will not get. You can calculate out the specific surface from this and also from this, they will not match, never, two methods do not match. So, they are relative, means for relatively comparing two different pozzolana, also two different cements. Specific gravity is the other important property that you would like to know, and then of course, chemical composition. Oxide compositions, that we have understood that must be very, very important. Lawson ignition is one which is actually quite important, Lawson ignition. Now, what is Lawson ignition? What we do is we take the sample, heat it up to 1000 degrees centigrade for half an hour and keep it there for half an hour. So, whatever material, unoxidized materials were there will get oxidized, because it is in a furnace, in air furnace, air is there. So, it will get oxidized, and whatever can go away. For example, if there is unburnt carbon is there, that will go away as carbon dioxide. If there is some moisture, that will go away as moisture vapor, or it will just get out. So, there will be some amount of mass loss, there may be little gain in mass also. So, the net effect is a mass loss, and that is what we call loss on ignition. In fact, it is a measure of how much carbon, unburnt carbon is there in the system, and that is detrimental, because we do not want too much of unburnt carbon. It consumes a lot of water with the concrete, and therefore, it creates other kind of problems. So, we do not want really high loss on ignition. The code specifies, specification various even IS code for various specific pozzolana would mention, because we have codes for fly ash, we have codes for ground granulated blast furnace slag, and we have now a code for silica fume. So, they specify what should be there, and this is what we measure. So, that is how we characterize pozzolanas. The most important characterization of course is pozzolanic activity, that means how much reactivity it will have, and one of the ways we measure is called lime reactivity. One of the ways we measure is called lime reactivity. This I like to highlight, this is measured using what is called lime reactivity. Okay. Right. All right. So, let us see physical characteristics. Right. I mentioned physical analysis, physical characteristics of all this analysis of pozzolana is done using IS 1727. This is what it is, Blaine's permeability method, lime reactivity, this is pozzolanic activity, specific gravity and particle size distribution. So, that is what is done, right. So, it is specified what should be the limits, how much minimum Blaine's permeability should be there, or surface area calculated from Blaine's permeability, what is the minimum lime reactivity. Let me just mention something about this lime reactivity. What is done in this case is, or similar other tests are there, this is one of the tests for pozzolanic activity. Lime reactivity is nothing but you make again standard cubes, in this case 5 centimeter by 5 centimeter by 5 centimeter cube, you make cubes of 5 by 5 by 5 cubes, and this you make with lime, cement, lime and silica, or your pozzolana, lime, silica, pozzolana in a given manner, roughly 1:3, but it would depend upon the specific gravity, and then add standard sand to it in a given proportion. Make this cube, cure them in a standard manner for 10 days, to 48 hours just covered under glass, another 8 days in a specific relative humidity and temperature, and then test them under load for crushing strength. Again, testing is also in standard manner. In other words, it is the making of the casting of the cube, casting the cube, curing the cube, testing of the cube, the materials used in the cube, all are standardized except the pozzolana, which remains as a variable. So, you finally find out the crushing strength at that age, 10 days or whatever it is, and there is a minimum value suggested for use in cement, for use in concrete, use in cement, use in concrete, etc., etc. So, these values are expressed in MPa, and strength of 5 centimeter cubes, 5 centimeter cube, and this strength is specified, and that gives us how how it would react with the lime. Is it good pozzolanic? Because a finer pozzolana with high reactive, more amount of reactive silica will show you high lime reactivity. There are other ways to measure this pozzolanic reactivity as well. For example, you can have cement reactivity, you can have pozzolanic activity index through concrete cubes and several others. So, this is what is done to characterize the fly ash. Let us see properties of some of those pozzolanas, the 3 main pozzolana I was mentioning. Let us say fly ash. Now, I mentioned there are 2 types, there are other ways of classifying fly ash again, and since our time is restricted, we would like to keep it to this ASTM classification. ASTM, that is ASTM, which is American Societies of ASTM type F, F and C, these are the 2 types. So, type F, type C, this is a classification based on ASTM, American Society of Testing Materials, and what they say is this classification based on the source of the coal. For example, lignite coal would give you type C, which will have high calcium content, 10 to 40%, and this has got calcium content for type F fly ash never exceeding 10%, right, it is between this. Okay, so these are the ranges of oxide composition, as you can see, 35 to 60, 25 to 40, etc., etc. This is the main difference between type C and type F fly ash. In the northern India, most of the fly ash belong to this, whereas somewhere in the Konkan region you will have or southern part of the country, Neyveli, etc., etc., you will have close to them, if fly ash those are available, can be of those kind. Silica fume on the other hand contains very little of all other materials, no calcium oxide, no iron oxide, no aluminum oxide, very little, but mostly it is SiO2 because it is produced from quartz. So, it is highly rich in silica content. GBFS, it has got lime also, because lime is used to remove this. So, that is why it can show what is somewhat cementitious properties also. This can also show a little bit of cementitious property sometime, but this is purely pozzolanic, this is purely pozzolanic. So, these are their oxide composition. If we see the particle size distribution, fly ashes are 5 to 150 micron sizes. This is very fine, that is what I want to highlight. This is very fine, 1 to 5 micron size, very fine size, very fine size. So, its characteristics is very fine, rich in silica, highly pozzolanic, highly pozzolanic. Okay. So, this is the characterization or properties of pozzolana, some properties of pozzolana. And if we see their chemical composition in a diagrammatic manner, they will look like this, where this is 100% calcium oxide, this is 790 and so on and so forth, this is 0% CaO. So, if you go along this line, calcium oxide increases. Now, a P stands for pozzolana, it will have very little C, type F of fly ash, let us say, very little CaO, whereas S stands for slag, has got some amount of lime, some amount of CaO, lime, and OPC had got the 67% or whatever is the lime. So, if you distribute this 0 to 100 along this line, and then if you look at slag, slag is here, Al2 100% here, 0% here. So, 0% Al2O3, Al2O3 along this and 100% here. So, if you see Al2O3 is more or less similar in all of them, slag and fly ash, pozzolana and OPC, but you come to SiO2, that is SiO2 is here the third main oxide here, which is 100% here and less here. So, this has got maximum, the pozzolana has got the maximum SiO2, whereas OPC has got less, slag has got somewhat higher SiOC. So, this diagram shows you the chemical composition of the various kind of pozzolana vis-a-vis Portland cement, right. So, this is what the characteristics of pozzolanas are. Okay. Let us see what it does, what is this, what is its effect. You see, this pozzolana reacts with, this is the pozzolana, right, this is the pozzolana, this is calcium, it is because we know SiO2 is denoted by S, we denote it by S, abbreviated as S. So, S stands for SiO2. So, pozzolana is rich in SiO2 and that is what reacts actually. Now, we have seen that C3S reacts with water to form CHS gel and calcium hydroxide, that is we have seen in the previous lecture. Similarly, C2S also reacts with water and produces this and CH. Now, when you are adding cement and pozzolana together, cement will react with water producing lime, and this lime can react with silica, in this case of course pure silica, and water producing same CHS gel. So, that is what it does. So, if you add a little bit of, or I mean if you put some amount, if you mix cement and pozzolana together and then add water to it, the cement will react fast and then produce lime. Once the lime has been produced, this lime can react with the pozzolana producing more CHS. What it is doing then? It is actually removing the non-sealing precipitate calcium hydroxide, which was useless really from that sense, from strength point of view or cementing property point of view, and CHS gel is the one which gives you cementing property. So, it is actually producing more cement to give you cementing property. So, therefore, this is what it does, this is what it does, right. Okay. It gives you crystalline outer product, I will just mention what it is, and then it gives you what is called a filler effect. Filler effect is given here, filler effect is given here, it fine material. So, go into the pores of the cement itself, right. So, this is what is called cement. Yesterday I mentioned to you about the hydration process of cement. If this was the original cement grain, if this was the original cement grain boundary, if this was the original cement grain boundary, then as the reaction progresses, grain boundary will change to this, because this material might have reacted with water and the product settles here, but some product goes outside also. This is called expanding cluster model. Now, we can use this model to depict the reaction of pozzolanas now. Say hydration of Portland cement will produce, this is the Portland cement, P stands for unhydrated Portland cement, this is the hydration product and some product will come here. This is again another particle of Portland cement, this is one particle of Portland cement, these are the aggregates and these are the aggregates, and the hydration product will accumulate here, which will also include calcium hydroxide. If I go to the next slide, hydration of cement and blast furnace slag. Now, slag is partially cementitious. So, this is my slag. Since it is cementitious, some product will form here also, but the pozzolanic product from the calcium hydroxide that was produced earlier with the silica here would fill in this space. So, you can see it will have much lesser void, and aggregates are here, this is the aggregate and this is the aggregate. Let us go to fly ash or some other pozzolana. In this case, you see pozzolana it is not cementitious, so this is the fly ash, it only gets consumed, but the space between the cement particles are now filled in by the additional CHS gel. So, it will have a much denser structure. So, that is how these three materials work. This three material works, this is how this three material works. What they do? They actually will give you better strength, reduce down the porosity, capillary porosity. So, therefore, they will improve the strength. Since the capillary porosity is reduced, durability is more, better durability, nothing can come in. Supposing you see the 28, but one thing, if you replace part of the cement by pozzolana, its strength gain will be relatively lesser, because pozzolana has to wait for calcium hydroxide to produce, and its process itself, reaction process itself is slow, I mentioned earlier. So, therefore, this process is relatively slower process. So, initial strength gain is less, but long term strength is very, very high. So, with Portland pozzolana, with Portland cement and pozzolana fly ash, strength, long term strength is much higher, better durability, but initial strengths are relatively less. Silica fume, if you can see, it refines the pore sizes significantly. Without silica fume, the pore sizes, the porosity would be this much. The porosity would be, without silica fume, the porosity would be this much. This would be the volumes of total volume of pore. But if you add silica fume, this pore volume reduces down. Also, the sizes in with silica fume ranges from this to this, whereas overall sizes was original something like this. So, both these materials, they actually improve the porosity and therefore long term strength. Now, what are the benefits of this material? Therefore, sustainability, this gives us sustainability. You are using less of clinker, less of carbon dioxide you are producing, you are using otherwise waste material. So, this is more sustainable. High volume fly ash concrete is one such example, where you use as much as 50% fly ash. Very strong high performance concrete can be designed by use of silica fume, because it can reduce down the pores to a very, very fine size, a very low total porosity reduces. And we have seen yesterday that these are the main factors which controls the strength and durability of concrete. Therefore, high performance concrete can be produced with this. Very high strength cement based materials are produced with silica fume, but remember, silica fume is costly and research cash potential has to be still seen. So, if we summarize now, we have talked about cement type, we have also mentioned about lime a little bit, but we have discussed something about supplementary cementitious material, and we have talked about their use and advantages, right. Well, I think that is all for the day. Thank you.